This is the video introduction to Experiment 4, Calcium Determination by Complexometric Titration. Your goal in this experiment is going to be to determine how much calcium is in an unknown liquid sample. You're going to express your answer in parts per million of calcium carbonate. This is the way that water hardness is expressed. The method that you're going to use is a complexometric titration using EDTA as your complexing agent. You're going to make your titrant solution, EDTA, and you're going to standardize it, just like you did in Experiment 3. The difference is, this time you're going to have to make your primary standard solution as well. You're going to get a whey bottle full of calcium carbonate, your primary standard. You're going to turn that into a solution of calcium chloride, and then use that to standardize your titrant. The reaction of interest in the standardization and the unknown determination is the reaction of free calcium ions in solution with EDTA to form the calcium EDTA complex. The indicator is the calmagite molecule, and this molecule is also a complexing agent for calcium and magnesium and other +2 ions. When it's complex to calcium in solution at pH 10 or above, it's red. When there's no calcium for it to complex to, it's blue. So what you're going to look for is this transition from red to blue. Your unknown is going to be a few milliliters of calcium containing water in a 500 ml volumetric flask. And so when you get it, all you need to do is dilute it to the mark and then mix it well and use it. So a little bit about complexometric titration, since you won't have done this in lecture yet. Your textbook, Chapter 11, deals with complexometric titrations in general. Specifically, EDTA titrations are in sections 11.2 and 11.3. In general, for a complexometric reaction, you have a metal ion, M, forming a complex with one or more ligand molecules, which are L in this. The equilibrium constant for this reaction gets a special name. It's the formation constant, Kf. And we want it to be large. So you should remember from general chemistry that a large equilibrium constant means that the equilibrium is shifted way to the right towards the products. And so that equilibrium arrow is essentially not really an equilibrium, it's just a right arrow, just a regular chemical reaction. That's important for a titration because we want to know that our reaction mostly goes to completion so that our stoichiometry is predictable. So L and M, again, represent the ligand and the metal ion. Ligands can be monodentate or multidentate, and the difference is in how many electrons they use to attach to the metal. So monodentate ligands attach through one electron pair, and multidentate attach through multiple electron pairs. The reason that we care about this is because multidentate ligands have this one-to-one stoichiometry usually, no matter what the charge on the metal ion is. And EDTA is multidentate, so we can be assured that the stoichiometry for when we do our titration analysis is going to be 1-to-1. So the formation constants for a 1-to-1 reaction, you write them just like you would write a regular equilibrium constant or a reaction quotient. We do have this 1-to-1 stoichiometry for our reaction, so you can just plug in wherever you see an L, plug in EDTA, wherever you see an M, plug in calcium. And so you should be able to figure out the formation constant that way and figure out if it's large or not. The problem is that only certain forms of EDTA can complex with the calcium ions. Only one certain form, actually. The rest of the EDTA that's in solution, if it's in a different charge state, can't form this complex. So we need to amend the formation constant in some way to reflect that. And the way that we do that is with the conditional formation constant. And this acknowledges this fact that some EDTA in solution can't bind to calcium to form the complex. Only EDTA that's in the Y4- state, so Y being EDTA in that equation, can complex with the metal ions. So the fraction of EDTA that's in the correct form is denoted by this alpha Y4- term there. And the size of that number, the magnitude of alpha Y4- depends on the pH of the solution. So we can buffer the solution so that alpha Y4- is basically a constant. That means it comes out of that equation rather, and we get this expression for Kf prime. which is the alpha Y4 minus term times the original formation constant. So if we know what fraction of EDTA is in the correct charge state, we can predict what Kf prime is going to be, and we can predict whether it's going to be big enough for our purposes or not. So to do that, we're going to control the pH as we do the experiment. The first thing you're going to do in your experiment is going to be to make EDTA solution. So you're going to weigh out some EDTA, dissolve it in deionized water, and then you're going to add ammonium buffer. This is how we're going to control our pH, and we're going to check the pH many times throughout this experiment to make sure that we still have enough EDTA in the correct charge state to give us predictable stoichiometry. To test the pH, you don't just dip pH paper into the solution. You dip your stirring rod into the solution, touch it to the pH paper, and then read the pH while it's still wet, just right away. The color will change over time. So your EDTA solution you're going to transfer from that beaker to a 500 milliliter volumetric flask, dilute it to the mark, and then you're going to transfer it to another container, because the next thing you're going to do is make your primary standard solution in the same volumetric flask. So you'll wash it out, weigh out the appropriate amount of calcium carbonate into the flask, and then follow the directions to make that solution. All right. You'll also want to check the pH of that one to make sure that it's around the correct pH. So when you have your primary standard solution, you'll pipette into a 250 milliliter Erlenmeyer flask. You'll add the Kalmagite indicator, and it will look like this. This is the wine red color that you should be expecting. As you add EDTA to this, the red is going to be removed, and it's going to be replaced by blue, free Kalmagite molecules. And so in the transition between all red and all blue, you're going to get purple. And it'll start out as a dark purple, and it'll transition to this light purple. And a lot of people like to stop here. They say, okay, there's no more red, it's done. This is not what the endpoint of your titration looks like. If you can see purple, that means there's still red in there. What you want is blue, the total absence of red. I know that this is a difficult thing to see, but now you have a picture of it. Hopefully you'll be able to evaluate this better while you're in lab. You're going to do this for the standardization, and then you're going to use basically do exactly the same thing, except you're going to pipette from your unknown flask instead of from your primary standard flask to do the unknown determination. So your data analysis looks the same as it did last time, really. You're going to calculate the number of moles of calcium that you added with the pipette when you pipetted out of your primary standard bottle. You're going to use the balanced chemical equation to find the number of moles of EDTA that you delivered with the burette at the equivalence point, and then use the volume of EDTA to find the molarity. Once you've done that, you do your unknown determination, and then you just do this calculation in reverse, essentially. You calculate how many moles of EDTA you delivered with the burette based on your volume and your molarity. Use the balanced chemical equation to find moles of calcium in the titration flask, which contains 50 moles from your volumetric flask of your unknown. And then use the volume of the unknown used to find the concentration in ppm of calcium carbonate. Remember, you're expressing your results that way, not with percent or molarity or anything else.